a case, it will convert like a unbypass system and you can find out the answer. Where you are seeing from there the transistor को equivalent neighbor none. Okay, which transistor you are not seeing the transistor को make it as an active load and solve this type of questions. Okay. From previous class में input has taken as an amplifier. Okay, and below that we have the ground and we are seeing from that the load. But इधर किधर से देख रहे हैं active load से देख रहे हैं. That's why ये load बना है हमारा active load. The transistor kept as transistor. Okay, slight difference is there between that idea and this idea. So what about the last one more case is there? That is the final case I'm teaching. Case 3 knowledge. Case 3. Case 3 is talking about bandwidth of cascode concept. So how to understand the bandwidth of cascode techniques? First, suppose I have taken an example of a common emitter amplifier. Suppose this is your ground. We have a resistance here RC. This is your VCC, and you have the output. This is your input. For example, I said that in this diagram, given data is RC is equal to 1 kilo ohm suppose, and small re is 1 ohm suppose. So dynamic resistance in the problem is 1 ohm. Okay, and load resistor is 1k. I ask you a question that can you calculate what is gain of this circuit? The simple answer is sir minus GM into RC will be the answer, sir. It's a bypass system, sir. So many times this formula we are using, it has already went into our mind, sir. Number of times you are writing same formula. Yes, same formula, minus GM into RC. But GM is not given, RE is given. Then we know the trick. GM is equal to 1 by RE we can write. Okay, GM go 1 by RE minus certain. So answer is minus RC by small RE you can write. So it is minus 1 kilo ohm by 1 ohm. Answer is minus 10 power 3. Up to here, the story is very smooth to complete. Up to here, the concept is very clear. Now somebody asks me, can you calculate the bandwidth of this concept? Then if I want to teach bandwidth, what I have to do is, bandwidth is always calculated from input time constant of the device. Input time constant. Tau I. Input time constant. Bandwidth is always calculated from input time constant of the device. So always remember, you will have input time constant and output time constant also. But output time constant is very negligible compared to input time constants. That's why in any problem, if you ask me bandwidth, I'll investigate the input time constant. That is rule number 1. In this problem, what is input time constant? Seeing the board. Your input time constant, if you see, it is Ri into Ci will be the answer. Ri and Ci. How much input resistance is there at the input and how much capacitance is there? Your Ri is nothing but R pi is the input resistance for the bypass systems. And what is Ci? In previous class we have seen it is CD plus some CD into 1 minus AB. So this is the way you got some Miller's capacitance in this concept. You got some Miller's effect here. Not only CD will be there, there will be transition capacitance will fall at the input side. That is CD into some 1 minus AB. I don't want to repeat that again. Okay? Miller's theorem we applied. Yeah, Apita, when VA is not equal to infinite, this tricks we are using. So you can write this answer as R pi, your time constant, we are getting like this. Your R pi into CD into 1 plus AB we are getting. Why it is cutting 1 plus AB means the gain is negative here. Negative of negative, it will become positive. So that means CD is a very small capacitance inside the transistor. It is getting amplified by 1 plus AB times due to Miller's effect. This is due to the concept of Miller's effect. Miller's effect. This gain is around 10 power 3. Your capacitance is amplifying. If the capacitance is increasing more by the gain A, then automatically the time constant will be very high. If the time constant is very high, can I say that your omega bandwidth is nothing but 1 by time constant of your input. If the time constant is becoming very high due to Miller's effect, your bandwidth will be very less. So this is the proof I can tell you why common emitters will use less bandwidth is due to some technical problem called Miller's effect in technical words. 1 plus AV times your capacitance is getting amplified. As the capacitance increases more and more, the time constant will increase more and more. As the time constant increases, the bandwidth will decrease. Natural. So that's why common emitter main disadvantage is it has a good power gain, high power gain, but it has a very less bandwidth. That is the trouble here. So but the trouble can be easily solved by cascode technique is telling. So what a cascode can do with this mathematics. If you see the cascode technique, if I take a cascode now, this is your transistor. You have input here, VIN. And the load, if you see correctly, your transistor is becoming a load here. This is Q2, this is Q1. This is your output. If you correctly see the cascode technique now. In cascode technique, for my first transistor common emitter, what is the load? Means this is becoming the load. Called transistor is becoming the load. So can I say that this is working as an active load here? This is behaving like an active load for your common emitter in this case. Whenever it works as an active load, what will be the Rx here? You have to write the equivalent for this transistor. If I want to know what is Rx, seen from the emitter of common base. What is common base input impedance? We studied in our previous classes. Your Rx will be equal to simply 1 by Gm because common base input impedance is low impedance. That is your active load impedance. So that is the active load technique. So what is your answer now? Gain formula will change. Your gain formula is AV1. First transistor gain will change here. That is minus GM1 into Rx. This is your gain of the common emitter system in cascode. So this is the difference we are getting. This is a common emitter, that is a common emitter in cascode. The first transistor gain is minus GM1 into Rx. It is minus 1 by RE1 into Rx is 1 by GM. So if I take both GMs are same, no need of writing here once. You can leave it out this, You are getting like this. Minus 1 by RE into 1 by GM. So I can write this answer as simply minus 1 by RE into RE, opposite RE. So answer is simply minus 1. So can you understand that in cascode system, the common emitter gain became minus 1. In your normal load, passive load, whenever I take, the gain became 10 power 3. There's a lot of difference between these two gains. In this case, we got 10 power 3. In that case, we got only minus 1 because there it has active load. Whenever active load is there, the influence changes to minus 1. But if there is a passive load, we are getting very high gain here. So less, what is the advantage of this is your time constant will change again. This is R pi, input time constant again, I'm solving. This is R pi into CD plus CD into 1 plus modulus of AV. AV1 we have write. In place of AV we have write AV1. So AV1 here became 1 now. Here became 1. So in this case 1. In this case we have 10 power 3. Now you can see the difference between these two capacitances. One side the capacitance is CD capacitance is amplifying by 10 power 3 times. But in the other case it is amplifying only by 1 plus 1 time. That is 2 times. So that means the amplification is going very high in case of normal classical load technique. When I go for active load technique, it is just amplifying only by 2 times. So the capacitance will not increase much. If the capacitance is not increasing, the omega of bandwidth with respect to time constant, if you see, the time constant is less, so bandwidth will be high. So this is the story. So Miller's effect became negligible in the second topic. So that is the main reasons why a cascode system will always give high bandwidth. Okay, high gain also is coming, high bandwidth is also coming. So that is the main purpose of using this special topic in our electronics. So this is my background scientific analysis to teach for the student why this is enjoying more bandwidth, why this is not enjoying more bandwidth. A common emitter have more time constant, a common cascode have less time constant because of these issues. With this I have been covered successfully this concept. Just one more hour is there to cover the last topic called Darlington pair. That will be the completion of this course. So last module is Darlington pair is there. Let us write the application for this. So what is the importance of this topic? Let us write a conclusion and we'll start doing the final analysis. What are the main properties of a cascode system with xenon? So write properly this one. So Anupam Das, you are thinking only first transistor gain. Overall gain is same as common emitter gain. I am talking about first transistor because we are talking only input time constant here. Okay, the first gain is less only. AV1 is 1. But what about AV2? AV2 we are getting a good gain. So total gain is high. The only thing is individual gain if you see in the cascode it is less. That is telling. Yes, Ashish, I think perfectly 1 p.m. the class will be completed today. For the Darlington pair is there now. Probably it is exactly. By 1 o'clock we'll round off the Darlington pair and exactly 1 o'clock I'll give the break. Don't worry, Ashish. Exactly, I promise you that 1 o'clock I'll give the break. Exactly, the timing is also going according to our content. Around 1 o'clock the class will be completed. Okay, on the multi-stage techniques. So 1 o'clock exactly you'll get the break. Don't worry. You can go for vaccination. No problem. It is 100% now. Be confident. You have to take vaccination. That is the reason now this COVID is not coming to our body. Okay, everybody is getting good stamina. That is the main reason we are not getting this COVID all these things. So everybody, please sincere advice, take vaccination. My 2 vaccinations are completed. You also take the vaccination so that there will be no problem for you. Yes, active loads are working like a practical current sources. Perfect. Okay, they work like a practical current sources. Very good, great. So let us write one conclusion for this topic. So write on the what you can say conclusion of this class, cascode class. Conclusion. So what are the highlights of cascode technique? Cascode technique main highlight is first point. A cascode will give high power gain with a high bandwidth. So both at a time, who wants? Better go for this amplifier. Who want high power gain with high bandwidth? This is a special IC we got. And second one, the output impedance, which are not for a cascode, is very high. So whenever you want a very high output impedance, better go for this one. So most probably where we use this application is, we use in generally TV receiver circuits. In every TV receivers, we have one IC inside. That is called cascode ICs we call. Okay, because at the receiver side, we have to receive all the signals. Nowadays, I think you can say so many channels are there. If you want to receive the channels, you must have required bandwidth. And at the same time, it has to get amplified both. So that's when TV receivers become a popular IC for us. Okay, so this is one. In current mirrors, whenever you want output impedance very high, then you can use cascode current mirrors are there, which are advanced mirrors, which is not in the syllabus. That's why I not taught you. But current mirrors generally they do with the cascode techniques because it will give high output impedance, which is important for a constant current sources. Yeah, in all the cases, Divya Das, in all the cases, power is getting amplified. In common emitter, you have highest power gain. The same highest power gain we can get here also. But highest power gain is there. But you don't have the, what you can say, power gain is high. We don't have the bandwidth for that common emitter. But common base, what happened? You have less power gain, but you have the high bandwidth in common base. If I join both at a time, you are getting both advantages. That is the mean. High voltage gain with high current gain is called high power gain here. Don't get confused. Common emitters will have common emitter system the advantage gain, high voltage gain you are telling. But at the same time, high current gain is also coming or not? Beta value. So beta into that will be power gain. Generally we think about power, not the voltage or current. Okay? High power gain is important. That is coming just like a common emitter. But bandwidth is not coming from common emitter. Common base bandwidth we are getting at the same time. That is the specialty of this topic. So come to the last topic today. That is the final touch I am giving. That is called Darlington pair. This is the final analysis. So by 1 o'clock we'll finish the theory part of this module. So keep the heading. Keep the next heading. Last topic. Sixth one. Darlington pair. Darlington pair. Darlington pair, which is called as common collector to common collector. One thing you remember, Darlington pairs we are not designing with MOSFETs. We are designing with BJTs only because the main purpose is to increase the input impedance. Already in MOSFET we have high impedance. Darlington pairs we don't want to design for that, especially for BJT classes. Darlington pairs we call. Okay, so Darlington pairs. So if I want to design a Darlington pair, it looks like this. You have a coupling capacitor. We have input. First common collector you have to design. This is biasing. Always the emitter should go as an output to the next stage. So you are going to connect here. This is another common collector. And we are taking the output at the emitter point. Like this. You can see a design of common collectors. This is Q1, this is Q2, two common collectors. Okay? Just see the junction points here. This is P1 here. This is emitter 1. But emitter 1 is going to E2 for the next transistor. And this is C1. And this is your C2. And this is your E2. So carefully draw this Darlington Bay technique. This is one common collector where the output is going to the next stage. This is also a common collector. So how to recognize a common collector is very easy. If you are taking the output across emitter points, this is output and this is output. We call common collector. Another rule is we have to see a short for the collector points, which will deal about a common point. This is the meanings I explained when I'm teaching common collectors. So this is called Darlington Bay circuit with biasing. Biasing is also there now in the circuit. So let us understand in this topic how to do DC analysis. First point. How to do DC analysis. रहमान इधर एप्लीकेशन अंडरस्टैंड के लिए कोई नहीं यार, आप क्यों कंफ्यूज हो रहे हैं? हाई पावर गेन विद हाई बैंडविड्थ बोल रहे हो, पूरा डेरिवेशन देकर दिखाया आपको. The common emitter power gain is coming here for us. At the common base का bandwidth we are getting here, both at a time we are getting, so that in TV receivers, whenever you are receiving some signals, it requires high gain and high bandwidth is required. He's telling. If you want high gain with high bandwidth, automatically cascode systems we are using. That point I explained here. In my confusion, क्या है? Clearly point to point I'm writing on the board. Okay, that's the meaning called cascode techniques. So and not only that, in current mirrors we can use, because high output impedance if you want, we can go for current mirrors. You can add that point also here. TV receiver circuits and in current mirrors we can use this. In current mirrors also you can use it. Current mirrors QS current means high output impedance we can get it. Cascode techniques if you use, we get a high output impedance. So TV receivers, current mirrors, all these things we can use it. Okay, this is called Darlington pair. Now let us apply the DC analysis for this. I'm doing DC analysis. If you apply DC analysis, the circuit looks like this. So this is your Darlington pair DC circuit. Okay, this is a DC circuit we are seeing. So how to write the current natures in the board? Current natures I'm writing. If you see from the above, there is one current is coming here is IB plus IC. Two currents will divide in the class. IB plus IC current will divide. This current will go this side as IB current, base current will go here to the biasing resistor. And one current will be joining here is IC current. IB plus IC at the collector point. And this IC current again will divide into two parts. One is IC1 current and one is IC2 current. So for two transistors, two currents will divide. Okay? And these two will have two voltage drops. This is VBE, base emitter voltage. Okay? And this also will have voltage drop. This you take VB1, this you take VB2. So we have two voltage drops here. If suppose VB is same, you can take same voltages. If the point zone is same given in the exam, you can take same answers. So this is the way I'm saying the concept. Whatever the current is coming here, this current is base current. But whenever it comes here, emitter side, it will become 1 plus beta times of IB current. So this is IB, this is IE. IE becomes 1 plus beta times of IB. Again, this current when it comes to one more emitter, this current will become here 1 plus beta times whole square into IB. You can see the style of base current how it is flowing. Each and every step, the 1 plus beta factor is increasing there. First case 1 plus beta IB you got when you are transferring from base to emitter. Again you have gone to one more emitter. Again it became 1 plus beta square into RE. This is the way first you have to understand the current movements. So this only we call it as operating current. This we can take it as your IEQ. You have to solve this current IEQ in the problem. Operating current at emitter point. So if you want to solve that IEQ, first IB how to write the answer. First IBQ how to solve it. Operating current at the base. If you get this answer, VCC minus VB minus VB, so 2 volts you have to subtract. So VCC minus of 2 VB you can write divided by VCC minus 2 VB divided by RB is there one resistor, RB plus one resistor is RB, not only one resistor, there are two resistors here. So it is 1 plus beta square times of 1 plus beta square times of RE. So the only difference from previous class to present is RB plus 1 plus beta times of RE is our old practice. Now it is 1 plus beta square times of RE in Darlington pair. So it is square times is coming here. So this is about your operating current how to find in a Darlington pair. So VCC minus 2 VBE divided by RB plus 1 plus beta square times of RE. When I know this answer, I think your game is over. IEQ will come from this slide. So IEQ formula will be simply operating current will be 1 plus beta square into IBQ. That is IEQ is equal to 1 plus beta square into VCC minus 2 VBE divided by RB plus 1 plus beta square into RE. So this is the operating current how to find in a common collector to common collector. So DC analysis is very simple. You need just a concentration how to write the currents relations. I think this is my information how to do the DC analysis. In the exams they may ask you DC questions or AC questions. You must be able to have the complete knowledge. So now the final job is AC part how to finish off. DC part I completed nicely. Now AC part how to complete I'll show you. In AC analysis we'll find out input impedance how much, output impedance, voltage gain, current gain, GM, all these factors we'll find out. That will finish the total content of this multi-stages. What book is there? Just a what book we have to finish off. Let's see after the break maybe. Because AC analysis will take no. some time to complete. If time permits me to complete up to before 1 o'clock, if you have 20 minutes also, we can start doing workbook. Because workbook may take half an hour to complete the workbook for these questions. It will not take much time. So workbook may take half an hour. So please complete fast. We'll finish within 15 minutes that AC analysis and we'll go immediately to the workbook for completion of this. So that afternoon we can start freshly a new topic called as differential amplifier module will start. Okay? So please tell me if it is completed. We'll go for AC to end up this concept. AC will take hardly 10 minutes, not more than, to finish this analysis. So it is completed. If you say, we can start doing the AC analysis now. So let us see the AC analysis. AC analysis. First have the rough diagram. What are the things you have changed in the AC model is the capacitor here CC is becoming short. Next we have the transistor. Next we have transistor which is connected to one more transistor and we have the load is RE. We have taken the output here V0 and this point became ground and this point also became ground because VCC should be grounded, so both are ground. The biasing resistor will fall to ground this side. So this is called an imagination how to understand the model, AC modeling technique. These two capacitors are shorted. So I am seeing a model like this. So how to represent this model, AC model by seeing this diagram? So it's easy, it's not a big issue. So first we'll write simply RB. You can see the AC model nicely. This is RB, this is VIN. So first you have a transistor model I am completing. This is R pi 1, this is R pi 2. We have in series coming. So we can have R pi 1 first. Next we have a current source will be there. This is GM1 into V pi 1. Next to bottom side we have R pi 2 will be there. We have second one, this is R pi 1, this is R pi 2. After R pi 2, we get a current source like this. We have a current source to this point, GM2 into V pi 2. And the collectors are grounded. In bottom side, we have here RE. We are taking the output. So correctly, if you observe, this is my AC model representation of Darlington pair. So I think previous slide, somebody is not completed that telling. So please note on it first. So somebody is asking to read this formula. IBQ is equal to VCC minus 2 VBE. I said, Rahman, I think you are asking. Who is asking this? Samresh. VCC minus 2 VBE divided by RB plus 1 plus beta square into RE resistance. That is the base current. Okay. Please Rahman, complete कर दीजिए quickly. Yes, sir, Parthasarathi, according to EDC concept, if IE currents, if I say that VBs are same, you said, correct? VB can be same, but IE currents can be different. What is the logic for that? Because IE is not only depending on VB voltage, it depends on reverse saturation currents. Because the formula is IE is equal to IS into E power VB divided by VT. So IE can change irrespective of VB or irrespective of your reverse saturation currents. So VB may be same, but IE currents can be different. Okay, according to the electron device concept. So try to have that knowledge. IE can be different. So if you see clearly now the points. So whatever the junction points you can see here, this is B1 here, and this is E1. So these two in between we have B1, this is E1. In between I have written R pi 1, here R pi 1, here current source, the transistor is over. So from emitter 1, you are connecting. From emitter 1, it is going to the next emitter 2 here. So from emitter 1 to emitter 2, we have the R pi 2. Here we have R pi 2. Okay, this is emitter 2. Emitter 2 to ground, we have RE. And we have a current source connecting for both the collector point to ground. This collector is ground. C2 is also ground, your C1 is also ground. So this diagram wise, I visualize your model there. That's called AC model. That's called AC model. It's very easy and comfortable. Just I want to know the calculations. Seeing the board, how I calculate here. Suppose if I want to know the answer from here, can you tell me what is your ZIN from here? Means as a Darlington pair, if you want to know, you calculate from the base, not from the RB. Because Darlington pair impedance means transistor impedance you want. So ZIN from there I want. So the formula you can write it as simply VIN divided by IB current. This is the IB current. If this IB is going here, it will be going as 1 plus beta times of IB. One step if it is decreasing, it will increase by factor 1 plus beta square times of IB. So the currents will go like this, one by one. First IB, next 1 plus beta IB, next it will be 1 plus beta square IB. If you have one more transistor, it will increase like that. So current gains will increase very good in this concept. Current gains will increase. So what is the input impedance seeing the board here is ZIN. The formula is very important. It is R pi 1 plus, you have to multiply 1 plus beta with that R pi 2. This is the second one. And just to multiply this factor with RE. So what is the special thing about this topic is, this is called special. So you can see the highest input impedance in our amplifier circuits. This is the highest input impedance. That's why a Darlington pair main purpose is wherever you have loading effect, it can easily solve by this circuit. Because this is my input impedance. It's an accurate input impedance I calculated, exact impedance. So this is a high input impedance device. High input impedance. Which can solve loading effect problems. So throughout your IC designs, we need Darlington pairs because loading effect is a common issue in cascading systems. Because one transistor to other transistor if you connect, that will become a load for the previous stage. That will create a problem for you in your analysis. To reduce that loading effect, better go for Darlington pairs. Okay? Darlington pairs are the better designs for you to get very high input impedance. At the same time, if anybody asks me what is the output impedance, seen from here. What is the output impedance? It's very common sense, it's very simple. From the emitter you are seeing, whenever you see from the emitter, it is from actual load concept, it is 1 by GM. So answer will be RE parallel to 1 by GM. This is a concept coming from actual load technique. जैसे act to load trick. Act to load trick से simple हो गया RE parallel to 1 by GM. That means it is giving low output impedance. It is giving low output impedance. So low output impedance already coming by common collectors. So whenever you want low output impedance, common collectors enough, cascode is not required. Darlington pair is not required. But to get very high impedance, better go for Darlington pairs. Darlington pair main purpose is not output impedance. Main purpose is input impedance. So these are the two issues we can think about. Two more issues I can write here. Two more issues. What is the gain of this concept? Gain AV is equal to AV1 into AV2. It's a two buffers for us. One buffer is another buffer is both are buffers only, voltage buffers. So AV you can write as 1. So AV is coming to be 1. So buffer is giving one answer. If you take two buffers, you'll get one only. If you take three buffers, you'll get one only. So it's a voltage gain is close to unity gain. So what about the current gain? If you see current gain, it is I naught by IB you take. So I'm not interested to calculate from the circuit. I'm interested to calculate from the base current. Suppose Darlington pair इधर से चाहिए तो I naught by IB you can solve. I naught is nothing but here 1 plus beta square times of RE divided by your IB. Sorry, 1 plus beta times of beta square times of your IB divided by IB. So the current gain is coming to be 1 plus beta square. So this is a current gain concept. Current gain is telling it will give high current gain. It is coming high current gain. So these are the main properties of Darlington pair. So but application wise if you see, this is my application. This is my application I use. This indirectly is an application. Main application is this one called loading effect to solve. We use this idea called high input impedance. So other things are basic properties which already we got in the common collectors. Okay, in basic common collector also we have output impedance low. Same thing we got. Gain is unity. That also same. Current gain became a double square. If the current gain becomes square, this answer is enjoying high input impedance. Because of current gain becoming more and more, your input impedance is also increasing. That's the main target. Summarize 1 plus beta term कैसे लिखा? This is IB my friend, and this current क्या होते हैं? This current is IE current, correct? So when base current is going to emitter current IE, it will be 1 plus beta times of IB. Again this emitter current becomes one more emitter current, then it will become 1 plus beta square times of IB. Like this I have written. So Parthasarathi here input impedance formula में कोई नहीं है. ये impedance लिया first R by 1, okay. Second ये impedance लिया R by 2, but IB if you want 1 plus beta extra multiply किया होता, that factor is increasing that. And if you go for RE 1 plus beta square I multiplied to get the input impedance. In equation Z 1 plus beta term. Yeah. 1 plus beta resistance कैसे है? 1 plus beta. Okay, 1 plus beta resistance कैसे है? These are all base currents here flowing like this. They're all base currents. That base currents, if you take common, it will become 1 plus beta times of R by 2, 1 plus beta square times of RE. These all IBs will get cancelled in the numerator to denominator. If you want, I'll write here. If you have confusion, you can have one more step here. Your input voltage, if you want to write these all things, IB you take common first. This is R by 1. This is 1 plus beta into R by 2 plus it is 1 plus beta square times of RE. So this is the way I'm doing actually. This is IB. So IB को common लिया यार, नीचे IB cancel हो जाते हैं, ये formula आ रहा है. Okay. Samresh, I think that is your doubt I'm expecting. IB will be cancelled so that the remaining factor will become your input impedance. So finally, I've been covered the 4 issues. There is one special case in this Darlington pair is GM. Transconductance is a special case. That last case I'll explain, with that we can stop this analysis. Transconductance. One time we'll see transconductance. Highlight these formulas. Keep the heading special case after this. One special case we'll try to finish. Yeah, WL will be neglected because it's a lower cutoff frequency. Shabni Das, वो पूरा previous topic में खत्म हो गया. Okay, WH will take, WL will be neglected when you're talking about bandwidth. Lower cutoff frequencies को छोड़ दीजिए, higher cutoff frequency consider. So can I feel that if it is completed, we'll come to the final step. That is a GM, how to calculate. Examiners will ask you GM concepts. In previous concept, GM, cascode technique GM became GM1. Now in this case, GM will become what? In Darlington pair. That is the final step. So neatly complete it. We are approaching to our final topic. So nice to complete all these things in the morning module. Great. We completed successfully multi-stage module. Rahman, how can you say that power gain is high in this topic here? Power gain कैसे high होते हैं? थोड़ा use करो logic. Gain is 1, he said. Current gain is high. Current gain high आ रहा है, but voltage gain 1 हो रहा है इधर. Because of one parameter is very less, other parameter is high. Power gain cannot be high. If you want more power gain, both should be high. Is required. Here we are not interested about power gains in common collectors. Our interest is loading effect problem solutions. This is the main interest for me. Unnecessarily don't make it power gain concept all this storage. Power gain is about comes in Darlington cascode techniques. Okay. So let us see the final issue. Let us see the special case I can say. Special observation case. Special case. What is the special case is? Transconductance knowledge. Transconductance. GM. How to solve GM? Try to see. Suppose if I take this is your Darlington pair. Suppose this is your Darlington pair. we have like this, given the problem. This is Q1, this is Q2, and make this as some ground. Now the point is, he has given some input here, Vin, and the output he has taken here, suppose some I0. Output is I0, input is Vn. Here we have some VB1 voltage from here to here, and here we have VB2 voltage. This is your AC drops. Now the concept is, what is I0? What is GM of the Darlington pair? CC to CC. It is equals to I0 by Vin, we can write. Seeing the board, you can write, it is a V0, I0 by Vin. Up to here, no problem. Output by input. But the input can be divided into two parts here. Input can be divided as I0 by VB1 plus VB2, you can write. VB1 plus VB2 you can write. But is it VB1, VB2 are same or different? If I want to teach this concept, first you have to find out VB1 how much. What is VB1 here? Is your R pi 1 is there here, your R pi is there here into IB current. So R pi you take same for both, R pi into IB. You take it as VB1. Is it okay? R pi, otherwise you can take 1, no problem. R pi 1 into IB. And what is VB2 drop here is? It is R pi 2 is there, second diode, which you have R pi 2. But here it is not IB, it is 1 plus beta times of IB. You clearly observe VB2, VB1, AC drops are not coming same. The first current is IB, second current is 1 plus beta times of IB. If two currents are different like that, then automatically your VB1, VB2 is always much greater than VB1 in this Darlington pair. Therefore the AC drop, whatever you are getting here, will be more than this drop, always. If the AC drop is more here compared to this drop, according to the equation, we can write GM of common collector to common collector as simply I0 by, simply you can take VB2 answer. In place of writing VB1 plus VB2, we have taken only VB2 because VB1 is neglected. So I0 by VB2 is nothing but your GM2 of your transistor. So the trick is very interesting to keep in mind. So what is the trick I understood is, if it's a cascode question given, GM1 will be the answer. If the Darlington pair is given, GM2 will be the answer. So one is depending on the first transistor, another application is depending on the second transistor. So this is the story of your complete analysis. With this I am stopping the analysis. Successfully we completed the theory part, is completed. In the workbook I think which chapters you have to cover today. After the break we have some discussion about the workbook. Then a new chapter will start. Break ke baad, we are going to start workbook. Meanwhile if you can start doing the problems by yourself, it's a good thing. I'll tell just chapter numbers for you. After completing your lunch, if you have some free time, you just refer these questions. Chapter number 6 of your EC book. Chapter number 6 of your EC book completely you have to solve. Chapter number 6. Chapter number 6 of EC book. And chapter number 8 of electrical book. Daily same, both questions are same. Only in EC we have some extra questions, 2-3 questions extra. So today I'll prefer EC book to solve it. All the questions remaining are same. So today order is EC book, I'll solve multi-stage amplifiers. Maybe after the break when I come, within half an hour we'll complete that workbook practice. After that we'll start a new module today called differential amplifier analysis today. Okay? That is our today job. So now happily you can take break. It is now I think 10 minutes to 1. I'm giving break up to 2 o'clock. I'm giving break up to 2 o'clock means you have 1 hour 10 minutes. In this 1 hour 10 minutes, you just take rest up to 15 minutes. Remaining 20 minutes, whatever the time I'm giving for you, just work out these problems so that when I start explaining the problem, easily you can get to the question. One time read each and every question, it will be registered in your mind so that I can do fast in the video lecture. Otherwise I have to be slow, each and everything I have to do, it takes time for me. That's why one time overview you can do for each and every question. Whether in my notes, is there any formula will be apt for that questions or not. You just try it, that's why 10 minutes extra bonus for you. So 10 plus 10, 20 minutes you take the time for this. So exactly 2 o'clock we'll start the class. Okay? 2 to 2:30. Half an hour or 45 minutes. We'll finish that workbook practice.